Welcome. In this session in linear data analysis, we'll explore how data flows through a simple model of an artificial neuron. Our simple model is a weighted sum, and what that means is that we have inputs, and we'll refer to those as X, and these, you can imagine, are voltages on the dendrites of an actual neuron. The weights, which we'll represent as W, are modulated by the cellular memory. And the bias, it'll be either the value beta for a very brief time, but usually in neural networks is referred to a bias scalar B. This we can think of as the threshold at the axon hillock. And the output, which is what the neuron responds to, is it will fire when the summed voltage exceeds this bias value. We can implement this in a simple computation by saying, and here it depends on which one we use, is we can either say that the weighted sum of the inputs exceeds the bias beta, or we can take beta over onto this other side, in which case we call it B, and we can say that the weighted sum of the inputs plus a bias scalar has to be greater than or equal to 0. This is the equation that we usually see in artificial neural networks. So what we'll do is let's imagine how data goes through this, and we'll imagine data beginning on the left and then going through on the right. And so this is what happens to our data, is that they start here and then they go through the summation process, and then there may be an activation function that in our case will be very simple, and then we get the output of the artificial neuron. This detailed drawing shows how we have each input multiplied by its weight, and then it goes into a summation, and then we're handling this bias term. In the actual neuron, it's something that happens around here, around the axon hillock, but in artificial neurons, what we do is we set or clamp a value at the value beta, and we're including beta or B, here it's B, we're including this in the weights that the neuron can learn, and the values that it's presented with are the values X. These go through a summation, and then we have potentially a transfer function. This is the detail. Sometimes when we just want to illustrate one neuron out of many, this is the kind of data flow that we'll have. So we'll have the inputs going through a neuron, and then we'll simply refer to the output of the neuron. So this computation is a weighted sum, and it's quite straightforward. What we'll do is we'll have an observation I, and we'll refer to it as a quoted vector, meaning that this observation isn't really a member of a vector space. It's usually an ordered list of real numbers. And then what we want to do is want to calculate the weighted sum for this input observation. And we'll refer to this as the scalar U. So depending on our context, we'll either refer to U as being a function of the input, or we'll just refer to the linear response of the input. And now we're going to start to tighten up our computation and say that we'll take that observation, transpose it, multiply it by the weight vector, and then we'll add the bias scalar. So now our neuron will fire if and only if this linear weighted sum exceeds 0. And in addition, since we'll be usually looking at artificial neural networks in the context of a binary classification problem, we want the user to provide us with a label for each vector. And if it's binary, we want them to be 2 labels. An important detail is that in neural networks, this label is binary, and it's usually referred to as 0 and 1. So you can think of this as being in a class and not in a class. It's in a class if its label is 1, and it's not in the conceived class if the label is 0. Let's note that this is different than other literature in machine learning, where we routinely use plus or minus 1. So when we go to read anything in neural networks and machine learning, one of the details we must attend to is which label is being used in that literature.